We started talking about edges. You can apply the Sobel-Roberts and private edge detector, declare whether a given pixel is an edge point or not. Laplacian of Gaussian, which is a more sophisticated edge detector, then Kenny edge detector, which was even better than Laplacian Gaussian. Then we talk about, instead of the edges, we just talk about interest points, which are like corners. And these interest points, in particular, we talk about Harris interest points and the Swift interest point. And then given those interest points, then we want to come up with a descriptor around a small neighborhood of each of the points. And Swift descriptor HOG, you learn about LBP and all those things are there, which are helping you to abstract an image, some meaningful symbols, meaningful descriptor to describe the image. What is an image? Okay, so traditionally in computer vision started looking into more features which are physically visible, like lines, rectangles or shapes and so on. So a straight line was one of the big feature in the beginning of computer vision. There were many line detectors and so on. And then other shapes are circles, ellipses, and it can be arbitrary shape. You want to define your object and be able to detect. So we are going to talk about that, how we get these shapes using the technique called Hough transform. So we'll start with a line. So line, as you know, made up of points. These are the edge pixels. And suppose we have these 5 pixels there, and we are showing them in the image plane X and Y. And when we say we want to fit a line, which means we want to fit equation of a line to that, and want to find out the slope and intercept, the M and C of this set of points. Okay, and we have touched upon this. This can be done 3 different ways, and we have talked about 2 ways. Today we are going to talk about third way. So first way, we have been, talking again and again, the method called least squared fit. So we have, in that situation, we have more constraints or more equations than unknowns. As you know that in the straight line there are 2 unknowns, the M and C, slope and intercept. And in the example I showed you, there were 5 points, but there can be n points. So you of course have more points, and each point will give you one equation of a line. So you have lots of equations and only 2 unknowns. So that's called over constraint. Number of constraint, number of equation, number of points is more than the parameters. The other method we talk about what is called RANSAC, which is called random sampling and consensus method. We talk about in context of the fundamental matrix and a couple of other things. There the idea is that we only need the minimum number of required constraint or required equation to solve the problem. For example, in equation of line, we have 2 unknowns, so we actually need 2 points. Now the question is, which 2 points? And so the RANSAC, the way it works, that you randomly pick 2 points, solve the problem, fit the line, then find how good is that line, compare that with the rest of the points, and then if you're not happy, then pick another random the 2 points and keep going until you are happy. So it's called RANSAC. And the third one, which is the topic of today's lecture, is that where we have the under constraint problem, that we have a fewer number of constraints than the unknowns. And in this case, we have 2 unknowns for our equation of line. We will actually have 1 equation or 1 point. And which is very interesting way, very different way to solve this problem. And that's why the person who came up with, called Hough, Mr. Hough, he actually got a patent. He never had any paper. So it's the only patent, and it actually works pretty well. And that's why it's very popular in computer vision. So Hough transform looks at the problem where it's under constraint. We have fewer constraint or fewer equation than what's known. Okay, so again, the least square fit, what we want to do is come up with a line which minimizes the distance, the error from the point to the line. And way to do it, that if there's one line, then it's easy. So we know all the points lie on the line, just use all of the points, and then we come up with, this is our equation of a line, and we want to find out these unknowns, which are the m and c, such that for every point this equation is satisfied. Satisfied means that if I bring in this this term on the left side, then y minus mx minus c, and for each point it will become y1 m x1 minus c, second point will be y2 m x2 minus c, and so on. So I'll have series of equation, and if the m and c are correct, then this will become 0 because this is equal, so I bring another side, it will become 0. But that is not always possible, so it will have some error, and that error will be non-zero. Sometimes it will be positive, sometimes it will be negative. So we look at the error, and this is the error, and square it so that when we add those errors, they are meaningful. Otherwise, if we don't square, then some positive error, some negative error, we sum it up, they will cancel each other and be a problem. So that's why we are looking at the least square fit, which means we compute the error and square it, and then we find the solution such that that error is least. And that method we have discussed many contexts like that. Okay, so then, as we know, to find the m and c, we will differentiate this with respect to m equal to 0, differentiate with respect to c equal to 0, and we will come up with a solution. And these are the number of equations, and we can put them in a matrix form like this. The left side is b vector, which are the y's, coordinate of the points, and then we have here, these are the x coordinate of points, and these are the unknowns, small b vector. And again, this matrix A is not a square because the 2 columns but many rows. So we will do the pseudo inverse. We multiply transpose on both sides, and then this we can do the inverse, and the D, which is this thing, we will give you this unknown which contains the m and c like that. So it's very simple. So now RANSAC, again, just to summarize, because we have talked about this, which is random sampling and consensus. This method is very suitable when we have outliers. Outliers means that there are points which actually don't belong to that point, but due to noise they are there, and we don't know which are the outliers. The points which lie on the line are inliers, they are on the line, and the points which are due to noise, due to some reasons, they are called outliers. So if we choose the least square fit using the outliers, then the solution will become bad, because just one point can make a big problem. But RANSAC is good for dealing with outliers. Okay, so as I said, we will randomly select 2 points to fit a line, find the error between the estimated solution of and all other points. If there is less than tolerance, then quit. We have a solution. Otherwise, we'll go to step 1. Keep doing that. So now getting back to fitting line. So this is also called the segmentation, that we have in this image several lines. As you see, there are 4 lines in this rectangle. There are more than 4 here. So now if there was only one line, then it's easy. This problem was easy. But several lines, and we don't know how many lines are there, and which points to use to fit the line, that's a problem. So if you already segmented, we know all these points lie on one line, all these points on this line, then we can deal with. But that itself is a difficult problem. Okay, so therefore that's will lead us to Hough transform. Now Hough transform, the really advantage of Hough transform is that we can fit multiple lines without any segmentation, without separating which points belong to which line, which is very good. The least square fit will not work, which will have problem. Okay, so as I said, this is the patent, which is listed here, and so you can actually look at all the patterns from Google. So now how do we fit the lines? Okay, so we have an equation of line like this, and what we are going to do is rewrite this equation in the M and C space. This is the equation of a line in X and Y space. So M and C are slope, and X and Y are variables. We have points in X, Y space. Now if we rewrite this equation like this, C is equal minus X M plus Y, then this also is the equation of a line where in C and M space, and where the slope is minus X and intercept is Y. So which is, pretty interesting way to rewrite, and that was the whole insight about this. So which means that if I have a single point I, then that will result in a line in the C and M space with that slope and intercept xi and yi. Okay, so that's very important insight, that when you look at this equation like that, and that will help us. So one point in the X and Y space maps to a line in the C and M space. C and M space are the slope and intercept. Okay. So so then what's going to happen, that say we have these 5 points. So we'll take each of the point and map it to these points are in X and Y space. We'll take a point number 1 and map it to C and Y space. It will be line like this. This point will map to line like that, and so on, 3, 4, 5. Now what's going to happen, that these lines will intersect in the C and Y space, in C and M space, and that where they intersect is the slope and intercept of the line in XY space. Okay, because they have to agree on this, because this line have one slope and intercept, one value of C and M, and this, when we look at the one point here, this maps to a line here, and this has lots of possible slope and intercept. Then we get the second point, and this has lots of possible intercepts and slopes. Similarly, this has lots of possible, but then they agree on one, and that belongs to that slope and intercept of line here. So which is what we are doing. So in a way that each point will vote for many possible slope and intercept. Second line will map for other possible slope and intercept, and so on, third and fourth, fifth. So whenever they go through particular value, then we count 1 vote, and here we will have 5 votes, because there are 5 lines going through that, because there are 5 points. The other places will have 1 vote, or maybe 2 votes in some cases. So that's the basic idea of the Hough transform. So that's what we are going to do. So here's a more concrete example from, I borrowed this slide from another lecture from Norway. So as you see here, that we have 2 points. So one point is here, and another point is here, and this is the equation of a line like this. This is X and Y space, and they somehow say A and B, but we can assume M and C. So now this point maps to this line here, and this point maps to this line here, and they intersect here, and this is the solution for this line, which is slope and intercept. Okay, and so therefore the algorithm for Hough transform is very, very simple. They have about 3-4 lines. So what you do, you first is you want to quantize the space. Your space is the slope and intercept, which is the C and M. So you look at different possible values of C and M and quantize like in buckets. And so you start with the minimum value of C to maximum value of C, and minimum value of M to maximum value of M. Then you have an image which has edges, which are point. You know the pixels, which are edge pixels. So for each edge pixel, you go through the loop for different values of M you go to that equation which we wrote, and since we will loop through m, we know the xy from the point, we'll get the value of c. So that will tell you that for that particular value of m, for that particular edge point, what should be. And we will go to that particular element in this array, which we have quantized, and increment that by 1. So that will give you 1 volt. Okay? And we will do that for all the points. And when we're done, then we'll count the votes. Whichever element has most vote, that's the solution. And that's it. It's a very, very simple algorithm. Yes?
What kind of agitation method would be best? I think.
Yeah, I mean, you can.
Kenny or Laplacian, because we use the zero pressing, it's not a straight line.
Yeah. So I think that's the question that, well, if you have a very ideal scene where there are only straight lines, nice edges, then you can detect that, and I'll give you examples. But many of the real scenes, they're not very, very clear lines, and you may have a difficulty finding lines. Even though this is a very nice concept, a very nice method, and generalization of that is much more powerful. But that's precisely the reason that these days computer vision researchers are not really using lines, shapes, and so on. They are limiting the most of the work to interest points and the descriptor. In many cases, as you remember, last lecture, you are not even finding interest point, you are doing dense sampling. You just look at the arbitrary pixel and find a descriptor. So it's an interesting trend, but scientifically this is very important concepts which you guys should know. Okay, so let's look at now another way. So one thing you will notice that when you have this accumulator array, different values of slope and intercept, slope can be infinity, so will be a problem. So you cannot have array up to infinity. The other is that so in particular when the lines are vertical, slope will be infinity, you will have problem. Therefore, what we are going to do, we will use the polar form of equation of straight line, which is like this, which is p is equal to x cos theta plus y sin theta, and that is better than the other form of equation of straight line. And the p is the distance of a perpendicular from origin to the line. So this is a line, and the angle the perpendicular makes with this x-axis is theta, and this distance p. So the equation of this line is p is equal to x cos theta plus y sin theta. Okay, so this is a better form. And other thing is that theta is actually available from gradient. Remember that every pixel you get a gradient magnitude and gradient direction. So gradient direction is actually that theta, which you can use, which is good. So we have talked about we can find the gradient vector, then you can apply a Sobel or whatever Kenny and get magnitude, get direction, and then the transform will again be, we'll have accumulator array, which in this case will be theta and p. We'll have different values of theta, which are finite, 0 to 360 degrees, and the p, the perpendicular distance. So now we have a point xy, and for that point we know it's theta from the gradient, and we can just put in here, and then it gives you p, and we go to that particular cell increment by 1. So you see here it's actually faster because we are not looping through different values of m we were doing here. We'll just go increment, and that's easier, that's faster. Okay, again we will finish all the edge points and go to the maximum and find that point, and that will be the solution. So here are the examples, as you saw these different lines there. On the right side is the accumulator array of this picture, and we found these maximas in that, and these correspond to these different lines. Brighter is higher. and this one is theta, this one is p, and that's what you're going to do. So then you can go back and then draw a line. So this is one line, this is another line, and so on. So one more example now. Ideally, if the line is like this, there should be one maxima here. It's shown here. But when you add noise, then these points can be displaced, and then accumulator array may look like that. As you see that this doesn't have just single point maximum. There are several points here, and then even add more, then become like that, and that is the problem. So what you need to do is, there has to be some, kind of threshold. So here we have 20 points, but we have added noise, then the maximum number of votes, are decreasing because they are spreading out, and we have to keep that in mind. Okay, so another example here. So we have these three images, this one, this one, this one. Now for this one, the accumulator is very nice. It is just one peak. Again, these slides are from this lecture from Norway. And then you can identify the peak and then get the line. Now this is a more complicated shape. It has several lines. Not all of them are lines actually. It's curved here.
Can you show where the line actually is in the first picture? I only see white image.
This is the image.
Yeah, it's just white, and then I see underneath it says A line.
Yeah, we can see.
Oh, because this, I'm sorry, this is a projector problem, so I don't know. There's a line here.
Okay.
Yeah, that's so you should complain to replace. I mean, this has been happening, I think, last few years. Light, okay, let's try that. Yeah, resolution, because projector is old, is that right? Yeah, let's try to turn off the light.
Sorry, now that he pointed it out, I can start to
How about now?
the imagination gets a little better.
Yeah, but you will get the slides, so it's okay. Okay? So this is actually, that's the original one, but this is the real one.
Oh, okay.
And then you see little lines there, is that right?
Yeah.
And these are the peaks there. These are detected. Now if there's noise, there are lots of peaks and there are lots of lines. So that's the main point here, that is impacted by the noise. Okay, so how about, you can see this one? Okay, so this is a real world example of the image. These are your sawbale edges, and this is accumulator array, again degrees in P, and these are number of votes. The brighter is higher, and then you can go back and get the 20 most prominent lines which are shown here, and which correspond to maybe these ones. Okay. So the difficulties are, what should be the increment of theta and p, because this is a binning thing, and then if they are too large, you will have a lot of computation. You have to go through these loops, and in the so that's the problem. They will be spread out, and if it is too small, then due to noise, some of the lines will be missed. So, things like that. So that is about the fitting lines, and it's a very nice scientific concept to understand and make sense. Then this general method of transform in principle can be applied to any shape or any equation you can write, and whether you have some unknowns and some knowns, you can do this kind of process, which is pretty interesting. So let's say, how can we fit a circle to the points? So again, we have to look for the equation of a circle and how many unknowns we have. If we want to fit a circle of radius r, we want to find out the center of a circle, which is x0, y0, and the radius of circle, which is r, and this is the equation of a circle. So now we have three unknowns, so the accumulator array will be three-dimensional, which will be x0, y0, and r. And we can, as we did in the straight line, we fix the one of the parameter and loop through m. So we can do the same thing here, and then we will be able to increment the corresponding cells in that. So, and then we'll find local maximum. So the other thing we can do, that in this case also we can use a gradient information. As we use gradient information in straight line, it helps us, it reduces the loop by 1. So we can write down the equation of a circle in polar form also, which is also there. And so and we can compute the gradient, and we can use that one. Okay, so this is the equation of a circle radius r at center at x0, y0 in terms of polar form. X0 is equal to x minus r cos theta, y0 is equal to y minus r sin theta. And then that's it. So then you can apply this standard algorithm for Hough transform. Now we want to find the circle of radius r. So your accumulator array is three-dimensional. We have we actually want to find the circles of different radiuses. We want to find all possible circles of different radiuses. So this is one parameter, and we want to find different centers of that circle like that. So therefore we will loop through different values of circle, and then we already know the theta from gradient, and we know the xy. We'll find x0, y0. So our x0, y0 will go to that particular element cell, will increment by 1, give a 1 volt, and then we'll find the maximum of that. Same algorithm, just replace these couple of lines, which is good. So if you do that, this is what you're going to see, that this is the image, and this is like your half space, parameter space, and then you'll find the center which corresponds to this. Now here we are finding the circle of only this radius. So the real image with these coins, and these are the edges. This is your parameter space, and we find maxima, and you can find these kinds of things here, which is fun. So now, and you can do this for ellipses, parabola, anything you can do, just keep going. And then actually I will ask you in exam some of these kind of questions, so you need to fully understand this. So now you can extend this to shapes for which you don't have equations, for which you don't have equations, and this is called generalized Hough transform. Okay, so generalized Hough transform, we don't have analytical expression, and it requires training. So through the training, we are going to get that information equivalent to the equation, and we will want to detect or fit those known object shapes, and that is in terms of the what we call the R table, and will be similar to what we were doing for circle. So let's look at this. Let's say you want to find in the image this kind of shape, and so you are interested in this. Okay, so you have examples of that before. So what you do, you find the centroid of, so all these points lie in this shape. You find the centroid of this, which is shown here, which is like a center of a circle, and this is a point lie on the boundary of this shape, xy. So now we want to find out the distance of this point from the centroid, and which is, you just subtract x coordinate from these, and that we'll call it R vector, which is like a radius of a circle. Okay, so, and essentially we will do this for every point on the boundary, and we will store those, and that is called R table, and that is equivalent of the equation of the shape like a circle or straight line. That's basically what it is. And of course we have a gradient information as we had before. So we'll construct a table of angles and R values, and which is shown here. So each of the point we have the R, and then it has angle theta, theta 1, and so there can be lots of points and they may have similar angles on the shape. So we will index those by the theta angle, 5 angles here, and all the R vectors with the same 5, we'll put them here, and again it's a two-dimensional vector, and next angle, and so on. So that is the model of this shape which we want to detect. Okay, so then we have the edge points x, y, we have gradient angle, we generate a R table, and for each edge point we will store all this information in a table which we'll call R table. And now when we want to detect a shape, then we want to find where that particular shape occurs, which means we want to find our centroid. So again, our accumulator array is x0, y0, the centroid of that. So then algorithm is very similar to the before that we will do for this. First is we will have accumulator array, that's a two-dimensional array, the centroid, x min to x max and y min to y max, and we'll do the loop for every edge point. We know its angle from the gradient, and then this is the relation before that R was computed like that. So we'll xc plus x bar and yc is equal to y plus y bar. Then we'll go to that cell, xc yc will increment by 1. We'll do this for all the edge points, and we'll find the maximum. So it's a very nice, all these are in the same framework, similar algorithm, and we are doing different things. Yeah.
The x dash and the y dash, that is the R, right?
Yeah, that's R. Yeah. Okay. So that's that. And so you can ask, say, well, now what happened to if the shape is rotated or scaled? Then what you do, So this method will not detect that so far. But the answer is that we can actually introduce a rotation angle, this rotation around z-axis, and also the scale, how much is the scale, also two other parameters. And again we do the loops. So same thing, as you remember, that rotation around z-axis, if the xy are the coordinate before rotation, we are rotating angle alpha around z-axis. These are new coordinates, x prime, y prime. Okay? So scaling is just multiplication with some constant, x coordinate by s, y coordinate by s. So rotation and scaling can be represented this. This is called similarity transformation, if you remember from the previous lectures. So x bar is given by x cos alpha minus y sin alpha multiplied by s, and y prime is given by x sin alpha plus y cos alpha multiplied by s. So now, instead of using those original equation, we are going to use this equation x prime y prime, which captures the scale and rotation, which is again nice. So replace those things by this. That's two equation, just change that. So now xc is x plus sx, scale, and you can have even different scale for x-axis and different scale for y. Okay, then the rotation x prime cos theta and so on, and that's it. So then the algorithm will remain the same, no problem. See, so that's your attitude you should have. Life, there's no problem in life once you understand, just keep going. It's very logical, elegant. So we can do scale, we can do rotation, we can do arbitrary shape, and that's it. Any question I can answer. So this is a short lecture because it's too late, getting late here. Any discussion, questions? Yeah.
In case of fitting a line, suppose you have just 1 point. Will we have a maxima actually?
Yeah, 1 point only, 1 vote only. See, so what will happen? That see in your accumulator area there can be some elements which has very few votes. So then you don't want to get that line because line has to have some minimum number of points. So that's why you apply the threshold to accumulator array. Say if it's more than 50 or 100 points, then you can take that. Otherwise, it's just a noise. As you saw these accumulator arrays in this last case. Even here, see like there can be many points which are local maxima, but those are not meaningful. So these are the ones which we are able to find. So that's and same thing with the straight lines. This one, see here there can be many, but these are the top 20 most significant, which has the maximum votes. Okay, more questions? Yeah.
When lines are detected in this method, they are like infinite lines, right? They are not.
Yeah.
Can we modify it somehow to get segment of lines which can also be used?
Yeah, that's a very good question. So see this will find infinite lines as you are shown here. It's infinite line. So therefore, you want to, when you build accumulator array, then you can actually keep track of what are the points of voting for that particular cell. And then when you find the maxima, from there the slope and intercept. So you draw that line, but then only those points which are XY location, then do that. So that's the way to deal with that.
Is it not good for the diagonal direction? It's very good for the horizontal and vertical, but it's not very straight for the diagonal in this way.
No. This is just the aliasing of the this old book. It shouldn't be because it's just angles. It should not be sensitive to that. Because in the old days when you want to low resolution, so diagonal lines as aliasing becomes curvy. More questions? No question. So this is this is a nice thing. What I like about this, and actually I learned this from my former advisor in Michigan, and I think he's the one. He explained these 3 different ways. The over constrained, which you need the least square fit, then constrained, and then under constrained. So this is nicely fit into in all these 3 things now, and it's it's a very elegant way to put this knowledge in your brain that you have a you have a problem expressed in terms of an equation and which has some unknowns and knowns, and you have some data, so you want to find your unknowns. Remember this former Secretary of Defense, Rumsfeld, he used to call known unknown and unknown known. So there's a very interesting movie about him also. So anyway, so the question is that how do you find these unknowns? What are different methods to find these unknowns? And how many different constraints you have? So if you have more constraint, better it is that you know a lot. But the question is, in this case, when you want to fit lines, if you have lots of points, you can get a very good line. But question is, how good are those points? Are they correct points? If they are noisy points, they are outliers, then more actually is worse. Okay? Then the bigger question is, how do you know which points are inliers, which points are outliers? So that's the biggest problem with the least square fit, where you are using this, sum of a square of errors. Other big problem is that this will work only for segmented line, that we know these bunch of points belong to this line. But if there are multiple lines, we don't know which set of points belong to this line, which set of points belong to this line, and so on. Then there'll be a disaster, because you are trying to fit a line on the points which are for 5 different lines, so you will get somewhere in the middle, which is none of those correct. So now to deal with outliers, then you can, RANSEC is a good way to deal with it, because you randomly select the minimum number of points required and fit a line and look at the quality of line by comparing the error from the rest of the points, and you keep going, and ultimately you get a good set. Then that also in a way doesn't solve the segmentation problem. And in that case, you may end up selecting points, 1 point from this line, 1 point from other line, so you'll get a line like this instead of a line like this or that. So then Hough transform kind of give you a very interesting, way. Say, well, look at 1 point and enumerate all the lines which can go through that point. There are lots of lines. And of course, we have infinite number of these slope and intercept, so you have this accumulator array, which is possible values of slope and intercept, or theta and p. Then you go through each of the point, and that gives you all the possible lines, and they vote for each of the combination of slope and intercept. Then once you are done, then there will be local maxima in that accumulator array for each of the line. So then you can go back and get it. So that's very nice. Now the question is, say, well, it's fine, you can do lines, you can do circles, you can do ellipses and so on, but how about, some arbitrary shape like this one? This is not a circle, it's not ellipse. So, but you can take that idea and extend it. Instead of the equation, you have this R table, because you have a gradient, you have some concept equivalent to the centroid, which is center of these points, and then you look at the distance and do that. So that's the story.